Mull. The Akashi Strait is one of the most punishing stretches of water on Earth. Tidal currents run at over 4 knots. Typhoons arrive with almost seasonal regularity. And at its widest crossing point, the gap between the shores of Honshu and Awaji Island stretches nearly 2 miles. Engineers in the 1980s were asked to throw a suspension bridge across all of it, the longest main span ever attempted. What they could not fully account for was what the ground beneath their foundations was about to do. The need for the bridge was real and urgent. Ferries crossing the Akashi Strait had been sinking in storms for decades. In 1955, 2 ferries went down in a single typhoon, killing nearly 170 people, most of them schoolchildren. Japan's government eventually committed to a fixed link. The Akashi Kaikyo bridge would carry 6 lanes of traffic, stand on 2 towers rising over 280 meters above the water, and suspend a main span of 1,991 meters between them. It was, by a significant margin, the longest suspension bridge span ever designed. The engineering teams knew the strait was seismically active. They designed accordingly, or so they believed. Suspension bridges transfer their load through cables to towers, and those towers transfer everything into the ground. The foundations of the Akashi Kaikyo bridge were sunk into the seabed using caissons, massive hollow concrete cylinders lowered through the water and filled to anchor the structure. The 2 main towers sat on foundations roughly 60 meters below the water's surface. The design had been stress-tested against wind, wave, and seismic loading. Engineers had modeled the bridge to survive a magnitude 6.5 earthquake at a distance. What they had not modeled was a fault line running almost directly beneath the structure. Construction began in 1988. By January 1995, both main tower foundations were complete and the anchorages were in place. The 2 towers stood. The main cables had not yet been strung. On January 17, 1995, at 5:46 in the morning, the Great Hanshin earthquake struck. Its magnitude was 6.9. Its epicenter was almost directly beneath the Akashi Strait, between the 2 tower foundations already embedded in the seabed. The city of Kobe, just across the water, suffered catastrophic destruction. More than 6,400 people died. Entire neighborhoods collapsed. Elevated highways fell onto their sides. When engineers reached the bridge site, the towers were still standing. The foundations had held, but something had changed. The earthquake had moved the ground, not metaphorically, physically. The seabed shifted, and the 2 tower foundations, locked into that seabed, moved with it. Precise surveying after the earthquake revealed that the 2 anchor points had separated. The distance between the 2 towers had increased by approximately 1 meter. In a structure where every cable length, every hanger position, and every deck panel dimension had been calculated to millimeter tolerances, a 1 meter change in the span was not a rounding error. It was a fundamental alteration of the geometry the entire design was built around. The question facing the project was not whether to rebuild. The foundations had survived intact, a significant engineering achievement in itself, and a validation of the caisson design. The question was whether the bridge that had been designed could still be built across a span that was now 1 meter longer than the original specification. The answer required recalculating the main cable geometry, adjusting the lengths of the suspender cables, and remanufacturing deck sections to fit the new span. Every prefabricated component that had been sized to the original 1,991 meter span had to be re-evaluated. The final main span of the completed bridge is 1,991 meters, the original design figure, because that number referred to the intended span. The actual post-earthquake distance between tower centers had increased, and the cable and deck geometry was revised to match the new reality rather than the original drawing. The cost of the project had already been extraordinary before the earthquake. The full bridge ultimately cost approximately 500 billion yen. The earthquake did not add a collapse to that cost, but it added time, redesign work, and the replacement or adjustment of components already manufactured. It also added something harder to quantify: the knowledge that the seismic assumptions embedded in the original design had been tested by an event larger than the design envelope, and the structure had not failed. That outcome was not guaranteed. It reflected specific decisions made years earlier: the choice to use caisson foundations deep enough to reach stable ground, and the choice to build the towers before stringing the cables, which meant the most vulnerable long-span elements were not yet in place when the earthquake hit. There is a reasonable counterpoint to the story of the bridge's survival. The foundations held, but the earthquake exceeded the design basis. Had the epicenter been closer, or the magnitude higher, the outcome might have been different. Engineers and seismologists have noted that the Hanshin earthquake exposed gaps in how active fault locations were mapped in Japan at the time. The fault that ruptured had not been identified as a major seismic source in pre-construction hazard assessments. The bridge survived partly because of sound engineering and partly because the ground motion at the foundation locations, while severe, did not reach the level that would have overstressed the caisson structures. Distinguishing between design success and fortunate outcome matters for how the lesson is applied elsewhere. The Akashi Kaikyo Bridge opened on April 5, 1998, 3 years after the earthquake and a decade after construction began. It carries the Kobe-Awaji Naruto Expressway across the strait that had claimed ferry passengers for generations. The bridge incorporates tuned mass dampers in each tower, pendulum-based systems designed to absorb oscillation energy during wind and seismic events. It was designed to withstand winds of up to 286 kilometers per hour and earthquakes up to magnitude 8.5. Those specifications were revised upward from the original design, informed directly by what the 1995 earthquake revealed. What the Akashi Kaikyo Bridge demonstrates is not that long-span suspension bridges are immune to earthquakes. It demonstrates something more specific and more useful: that foundation depth, construction sequencing, and post-event geometric recalculation can together determine whether a structure survives an event outside its original design parameters. The 1-meter shift in the span is the detail that stays with engineers. It is a physical record of what the ground did, preserved in the final dimensions of the longest suspension bridge span on Earth. The earthquake did not stop the bridge. It became part of its measurement. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.